Hello, calculus class type people. Today we're going to be talking about optimization. Optimization is getting basically the either the shortest distance between 2 points, getting the most area out of your fencing, getting the most product for your money, getting anything that involves with maximums and minimums, really. So that's what optimization means. You want the minimum amount of something bad, the maximum amount of something good, right? Optimization just kind of makes sense. So what we're going to be talking about today involves a couple of different things. The first thing we're going to talk about involves distance. Example 1, find the shortest distance from this function, y squared equals 2x, to the point 2 comma 0. Now, before we get into anything else, I just want to take a couple of things real quick. Y squared equals 2x. Well, let's say that we were to solve for y so we could get an image of what this thing looks like. We'd have y equals plus or minus the square root of 2x, right? So what you would get then is a square root function with a top and a bottom. It looks something like this. You got up like this. You've also got down like this. And it wants to know the shortest distance between this function and the point 1, 2, comma 0. Now, let me zoom in for a second here because I want to talk about the shortest distance. We all know that the shortest distance between 2 points is a straight line. Now the cool thing about this is if you notice, I could draw a straight line out to here, but it wouldn't be the shortest distance. I could draw a straight line to here. It's getting closer, but not quite shortest. I could draw a straight line to here, and that's going to be my shortest line, and then it gets a little bit bigger, a little bit bigger. So the question is, how do you know where to draw the shortest line to? So how do you know what the shortest line is? Well, it has to deal with how it hits this other side. See, the shortest line is going to be the one that intersects this side at a perpendicular tangent to this line. So what you can see here is that if you could think of change, it's bigger, a little bit smaller, a little bit smaller, smallest, a little bit bigger, a little bit bigger. So the change is, if you go from left to right, it's decreasing and then it's increasing, right? It's getting smaller and then the change is getting bigger. Kind of like a minimum, like you're minimizing the distance. And that's what I want you to think about. Think of minimizing the distance. We'll call it D. Minimizing the distance. You want to find a minimum. Well, the same way we find any minimum, look at a derivative. Ooh, I need to back up now. Look at a derivative, see where it's 0. See where the derivative is 0. That's going to be either a minimum or a maximum. So I drew some different things here, some different shapes, different figures, just to kind of give you an idea. The shortest distance, let me just do all of them real quick. The shortest distance here, this is a little bit longer, a little bit shorter, a little bit shorter, shortest, a little bit longer, a little bit longer. All of these hit when the change becomes nothing. When the change becomes 0, then you found the shortest distance. So you're changing a little bit less, changing nothing, changing a little bit more, changing a little bit more. You're finding the minimum change value, right? The minimum change value. You could also think of it as a horizontal tangent, right? That's basically what you're finding here, a horizontal tangent. So that's extremely important to understand the concept behind what I'm about to show you. Now, to take a derivative, you need an equation, and I'm not talking about this guy either. I'm not talking about him. I'm trying to find the minimum distance, so I need a distance equation. Something like you learned back in algebra. x1 minus x2 squared plus y1 minus y2. I hit a 48. Squared, square root of all that. We're going to use this and come up with a value. The only difference now is I need this to be x and this to be y. What I'm trying to do is equate these two values into this function with these two values. Let me show you what it's going to look like. D is equal to the square root of x minus 2, x minus this point, plus y minus this point. Okay? So let's see what this will come out to be here. I've got D is equal to the square root. X minus 2 squared is x squared minus 4x minus 4 plus 4, excuse me. Y minus 0 is just y, so that's y squared. Now I've got to come up with a way. I've plugged in this point. Now I've got to come up with a way to plug in this information into here. I need a way to plug this into here. I've got the point in. Now I need this in. Well, here's my point right here. Or here's how I can do that. Plug in y squared. See this guy right here? Y squared is 2x. So what I'm going to do is come back and just say D is the square root x squared minus 4x plus 4 plus 2x. And now I can simplify a little bit. D is the square root of x squared, negative 4x positive 2x minus 2x plus 4. So I really want you to grasp a hold of what I'm doing here. I plugged in my point first, simplified a little bit. Now I plugged in this other equation. So you have to find a way to plug both of these into distance, into your distance formula back from Algebra 1. And what we're going to do is minimize this distance. Here's my distance. I need to minimize it. Now there's two approaches you can do to here. You're going to take a derivative and you're going to set it to 0 because I want to see when the derivative is 0, when the change is 0, just like I would to find a minimum. Now, there's two ways you can do this. You can do it with a really long chain rule with a power to a 1/2 and then bringing it down. But check this out. What if I squared both sides? And I got x squared minus 2x plus 4. And now I take the derivative. So what I end up with here is 2d prime. Don't worry about the implicit stuff or the other variables. It's 2d prime basically. Or you could even think of it as, forget the 2, just think of it as d squared prime is equal to 2x minus 2. The derivative of this, I'm trying to set to 0. So 0 squared, or 2 times 0, is all going to be 0. So I'm going to take my derivative, set it to 0, and solve. Now, if I had chose to go the other way, and you got d prime to be, this would be a really long chain rule. It's going to end up being parentheses to the 1/2 x squared minus 2x plus 4. Wow. You end up with 1/2 to the negative 1/2. Let me write down what this is going to end up being. And then the square root. Okay. You end up with this. and then you end up setting d prime to 0 because you're trying to minimize the change. Multiply this side to over here, multiply the denominator over here, you end up with the same thing. So why would I go through the trouble? That's what I did all that for. Don't go through the trouble. Every one that you do, you're going to end up doing this on. Squaring it, setting that d squared prime to 0. It makes your life so much easier. Just don't worry about it. Okay? So we keep going here, solve for x, so add 2, you get 2 is 2x, and x is 1. Right? Now that's my x value. I'm looking for a point. I'm looking for this point right here. Right? But if you notice, since this is an up and a down, there's going to be 2 of these. So I have an x value, and you'll see why there's 2 in a minute here. I have an x value. When I plug in this 1 in for my x values, oh, that's a little bright, I'm sorry. When I plug in x into here, a 1, I'm going to get 2 answers, right? So I plug in an x in here, y is plus or minus the square root of 2 times 1. The square root of 2. So I've got 2 answers for y. Now notice that these give me points. I've got an x value, I've got a y value. Those are points, but those aren't distances. To get my distance, I've got to plug them back up into my distance formula. So that's what I'm going to do right now. I'm going to take my 2 x and y, and I'm going to plug them in. I'm going to say distance is going to be the square root. Now I want to clarify something. The distances are going to be the same, right? Plus or minus doesn't matter. The distance is going to be the same to here as it will to here. It's only the points that are going to be multiples. So I've got 1 minus 2 squared plus, and then you have your 0, so plug in your y value, that's the square root of 2 minus 0 squared. So d is going to be the square root of 1 plus, this is the square root of 2 squared, which is 2, the square root of 3. The square root of 3 is the shortest distance from these 2 points, from this function and this point. The square root of 3. So again, big picture it. I started with my distance formula and plugged in my point that I wanted to find. Simplified a little bit, plugged in my equation. Simplified and squared it to get rid of the square root. That's an ugly square root and I don't need it because the derivative would get rid of it anyways. Take the derivative of this side, set it to 0. Solve for x, solve for y, plug them in. And there you have it. Now, one more from the next page. I'm going to try and do this one a little bit quicker. Now that we know what optimization is, it goes a little bit faster. It looks so dull for some reason. I'm not sure why. Oh, it could be because my brightness on my computer was turned down. Okay, so a Texas Ranger has an 800 square mile rectangular plot of land. That's an area. And he wants to divide it into 3 equal regions. Find the dimensions so that the rancher uses the least amount of fencing. He's a rancher. Not a ranger, but a rancher. Why not? He could be a rancher and a ranger. He wants to divide it up into the least amount of fencing. Times are hard. He needs to save money on his fencing. So here's what I'm looking at. Area is length times width, right? This is kind of like, let's say that this area or this length here is your x value and your width is your y value. So this is really like saying x times y, length and width, x and y, for area, right? He's 800 square miles, has to fit in this area. So I'm going to leave that for just a second. Back to how we come up with fencing. The fencing that you're going to use, well, you've got two of these x's here, and you've got 1, 2, 3, 4 pieces that are y. All right, this one's a little bit easier to understand. What I've got to do is come up with an area fenced in under these parameters. 2 x's and 4 y's. So what I'm going to do is try and figure out a way to plug this area into here so that I can maximize it. Because I have to have this area of 800. So what I'm trying to do is find a way to substitute this into this equation. Now, since I like dealing with x's, I'm going to solve this for y, which is 800 over x, and I'm going to plug this in for y. Fencing is 2x plus 4 times 800 over x. So all I'm doing here is getting my fencing in terms of x. I want one variable to deal with. That way I don't have to deal with all of it. Now I want to maximize this, so I want to find my maximum value. So I'm going to need to take a derivative, set it to 0, and see what kind of numbers I get. All right, so let's kind of simplify this a little bit here. We've got f is going to be 2x, 4 times 800 is 3,200, and let's bring that x up. That way we don't have to deal with a quotient rule. F prime is 2 plus, let's see, this will be a negative 3,200 x to the negative 2. And then we said we were going to set it to 0, right? 0 is 2 minus 3,200. Let's go ahead and bring that back down. Can't do anything solving with it being negative. Subtract your 2. Actually, you know what? Yeah, I'll subtract a 2. Minus 2, 3,200. Negative 3,200 over x squared. Let's get rid of the negatives. I don't like that. Divide each one by negative 1. You're good to go. 2 is 3,200 over x squared. I just divided by negative 1, got rid of them. Multiply by x squared to move it over here. And divide by 2. 3,200 divided by 2 is 1,600. Take the square root, and we get a plus minus 40. Do we need the minus? We were talking about fencing. Can you have a negative fencing? Nah. Positive 40. That's 40 what? Back up to the question. He has an 800-mile rectangular plot. That's a big plot. So this x needs to be 40 miles. Well then, simple enough. To get y from back up here, 800 over x. And that's going to be 20 miles. So 20 times 40 is 800, and that's going to give you the the least amount of fencing. 20 for x, 40 for y. So that's going to be 20, 20, wait, I'm sorry, 40, 40, 20, 20, 20, 20. That's going to maximize your area. All right? So again, to optimize, all you have to do is find a way to relate one equation to another. In other words, take this equation and moosh it into this one. Take a derivative, set it to 0, and solve for what you're missing. All right? Have a good one.